Hello, everybody. Welcome to today's session, live stream from the Princeton Review. So today's topic is Introduction to Proofs. So I'll talk about what proofs are, try to show you a bit what role they play in mathematics, and also some of them are just pretty cool. All right, so let's get started. So first of all, what is a proof? You may have this idea of a proof from geometry class. Even those of you who haven't taken geometry yet, you've probably heard from people who have, especially in the US in 10th grade or 9th grade when geometry is taught. There's this idea of a two-column proof, these tables of axioms and deductions which are possible from those axioms of geometry that you use to prove some sort of statement. But I want to make the point that proofs are much broader than just these two-column geometry proofs. A proof is any sort of argument or justification or reason why something must be true. So one way to put it is that it would be the answer to the question, why, when the person asking the question wants an argument which is indisputable, in the sense that any person who has enough time could understand the argument and be fully convinced by it. So for example, some facts cannot be proven. For example, why is the sky blue? Perhaps the sky is blue right now and we could measure it and things like that, but we couldn't prove it in the sense of mathematics because the sky could conceivably not be blue. For example, maybe we wake up tomorrow and the sky has turned orange. So there's no way to prove that the sky is blue purely from logic. On the other hand, if somebody asks you, why does 2 plus 2 equal 2 times 2? Now this we could prove. Or why is the area of a rectangle equal to the product of its side lengths? I could give you an answer that's impossible to argue with. So here's an example of a simple proof. P is true, where P is some statement. Then if P is true, Q must be true. Therefore, Q is true. Okay, so in mathematics, we start from simple axioms. An axiom is just a fancy word for a rule. Okay, that's all that means. Let me start using my tablet here. So axioms, that's just a fancy word for rules or assumptions that we make in the beginning. So in math, so for example, in geometry, there are famously 5 Euclidean axioms, which means 5 starting assumptions that the rest of geometry comes from. Those are things like 2 parallel lines will never meet, and so on and so on. Okay, and from those simple rules, you can prove everything else. Proofs are the mechanism that we use to build our knowledge of mathematics. Start from simple rules and then build everything else from there. All right. But I could definitely understand asking, why should I care? You know, aren't proofs just an annoying exercise in confirming something that we already know? Like, sure, maybe mathematicians need to know how to do proofs so they can invent math, but if I'm not going to be a mathematician, then why do I care? All right. I think there are some good answers to this. So maybe in math class, you find proofs fun and they could be a good intellectual challenge. But maybe you find them annoying. So in that case, I want to try to convince you, why they could be good. First of all, in the broader world, especially if we take a long-term historical perspective, proofs are extremely useful. They allowed math to build over time from generation to generation without backsliding. For example, when Renaissance thinkers rediscovered ancient Greek mathematics after the medieval period, would they really have been able to trust it or been able to understand it without proofs? But since there were proofs, which remember are just convincing explanations of the reasoning of the Greek mathematicians, we were able to build on that instead of having to reinvent starting from the beginning. So if you view math as this intergenerational long-term project, then proofs are the engine that allows that to be possible. On a more personal or individual level, proofs are also a way for you as a student to understand a topic more deeply. This could be rewarding in its own right, but it's also useful because if you understand a topic more deeply, you'll remember it better. And this will also help you avoid mistakes since you have a deeper understanding and to solve problems or have insights that wouldn't have been available to you otherwise. Um, More generally, outside of mathematics, doing proofs is also good practice in reasoning carefully and precisely. So maybe you were wondering why there was a picture of Abraham Lincoln on this slide about math. Abraham Lincoln was not a mathematician. He was a lawyer and he was the president of the United States. Um, um, Lincoln also was relatively uneducated as a youth. I don't want to get into the whole biography of Abraham Lincoln, I guess, although it's fascinating to read about, and I'd recommend doing so. But Abraham Lincoln, in his 20s, carefully studied Euclid's Elements, a textbook on geometry that was written by the ancient Greek mathematician Euclid 2,000 years ago. And by candlelight, Abraham Lincoln would stay awake in his log cabin or whatever, carefully studying the elements to learn how to think more carefully and precisely as training to help him become a lawyer. All right. Let's see some simple examples. Okay, let's make some proofs about even and odd numbers. These are principles about even and odd numbers that you may already know. So first, here's our first theorem together. The sum of any two even numbers is even. Tyle, I know you're thinking to yourself, Tyle, I know that's true already. Tyle, sorry, I'm Tyle, that's me, hello. Thank you for joining us. And by the way, feel free to ask any questions as we go. So just type any questions you have into the chat, and Shadna will pass them along to me, and I will answer them. But here's our first theorem, and you're thinking, Tyle, I know this already. The sum of two even numbers is even. Okay, so why is it true? Prove it. Why is the sum of two even numbers even? Okay, I'll show you how to do this first one. Okay, consider any two even numbers, x and y. So far, I'm just labeling the numbers in the problem, which is a good way to start. Okay, often the first step in a proof is just to label what's going on so that we're able to make precise arguments about those quantities. Because x and y are even, we can write them as x equals 2 times a for some integer a, and y equals 2 times b for some integer b. Okay, then I can add these two together. X plus y equals 2a plus 2b, substituting from the second line of the proof. And then I can factor out the 2 using the distributive property of multiplication. So I get that x plus y equals 2 times a plus b. But a plus b itself is still a number. So I just proved that the quantity x plus y is 2 times something, some integer. So this proves that x plus y is even, since what it means to be even is to be twice some other whole number. So since we didn't use any special properties of x and y, we only used the fact that they were even numbers, and we showed that their sum therefore had to be even. This shows that the sum of any two even numbers is even. All right, so I hope that reasoning made sense to you. We used the fact that x and y were even to prove that x plus y must be even. So now I want you to try this one. I'll give you guys a minute to try to figure this one out yourself. I'd recommend using a pencil and paper since thinking can be a little easier sometimes when you can write down the intermediate steps and not have to keep the whole thing in your head. So give it a try. Try to prove that the product of any two odd numbers has to be odd. We know from doing examples that when we add together two odd numbers, we get something odd, right? If we try 7, or I'm sorry, I said add multiply 7 times 9. If I multiply these, I get 63, which is odd. Any pair that I try, I always get something odd, but prove that it's true for all odd numbers. I'll give you a minute to work on it. Okay, no worries if you felt stumped. That is perfectly okay. If you did figure it out, congratulations. Let's go over together how we could prove that any two odd numbers multiply to a new odd number. First of all, I could try using a computer or something and just checking every pair of odd numbers, right? And just like 3 times 5, 5 times 7, 11 times 379, but I can never get them all. So here's how I could do it. Consider two odd numbers, r and q. So the first step is just that I'm going to label the two numbers like I did before. Okay, so now my two odd numbers are r and q. Because these numbers are odd, what that means is that r equals 2a plus 1 for some integer a. For example, if a equaled 1, then that would mean r equals 2 times 1 plus 1, which is 3. Or if a equaled 2, that would mean that r equals 2 times 2 plus 1, which is 5. Okay, so r equals 2a plus 1, and q equals 2b plus 1 for some integers a and b. Okay, a and b could each be, I'll say that, I'll say this, a and b could each be like 0, 1, 2, 3, and so on. Okay, but there's some value of a and b that I can use to write r and q this way because they're odd. Therefore, r times q is 2a plus 1 times 2b plus 1, just using the fact from the previous line. But then, if I FOIL out or multiply out these two binomial expressions, I get the following. The 2a and the 2b terms multiply to give me 4ab, and then the 2a multiplies with the 1 to give 2a, the 1 multiplies with 2b to give 2b, and the 1 multiplies with the 1 to give 1. 4ab plus 2a plus 2b plus 1. But now, notice that these first three terms can have a 2 factored out of them. So I've rewritten r times q as 2 times this whole thing, which I'll highlight in yellow, 2 times this whole thing plus 1. So the whole thing I've just highlighted is some new integer. So I've proven that r times q is 2 times some integer plus 1. And so therefore, r times q must be an odd number. So r times q is odd. And I wrote QED here. This is a fancy proof thing. It's a fun thing to get to say. You're allowed to say QED once you prove something. It's like an exclamation. It stands for, it doesn't really matter, but it stands for some Latin, which means, it's like quod erat demonstrandum, which means the thing which was supposed to be demonstrated. That which was supposed to be demonstrated, or the thing that we were going to try to prove. So we get to say, aha, victory, QED. Very exciting. It should make you happy to get to say, QED, I proved it. Let's do something a little more complicated now, counting the primes, but still not too bad. The primes were first counted by the ancient Greek mathematician Euclid, the same person who wrote the geometry book that Abraham Lincoln studied. And he did this more than 2,000 years ago. First, though, what is a prime number? A prime number is a natural number which is greater than 1, which is not a product of two smaller natural numbers. Natural numbers mean the numbers 1, 2, 3, 4, 5, 6, like that. Okay, so you could call them the positive integers as well. Sometimes 0 gets included. It's a little bit ambiguous. Okay, so a natural number greater than 1 that is not the product of two smaller natural numbers. So for example, 5 is prime. Could we prove it? How would we prove that 5 is prime? Well, To be prime means that it's not a product of two smaller natural numbers. And the only natural numbers which are smaller than 5 are 1, 2, 3, and 4. So we can try multiplying together 1, 2, 3, and 4 to see if we can make 5. And we could, since there's only a finite number of possibilities, here we could just try all the possibilities. None of them work. This proves that 5 is prime. On the other hand, 4 is not prime because we can break it apart into a product of two smaller natural numbers. 4 equals 2 times 2. So 4 is not prime. We call those smaller numbers that multiply together factors, and we say that they divide the number that they are factors of. So the first handful of primes are 2, 3, 5, 7, 11, 13, 17, and so on. Hope I didn't mess any of these up. Doesn't look like it. Prime numbers get less and less common as the numbers you are considering get larger. For example, there are 25 prime numbers between 1 and 100. But there are only 6 primes between 1 million and 1 million plus 100. So 25 between 1 and 100, and then just 6 between 1 million and 1 million plus 100. Each range is 100 numbers long, but there's only a quarter as many primes. Why do you think that is? Can you see why there would be fewer and fewer primes as the numbers you're considering get bigger and bigger? What do you think? Why will there be fewer prime numbers as the numbers get bigger? All right, so hopefully some of you might be typing your explanations into the chat as to why that's true. The answer is because the bigger the numbers get, there are more and more smaller numbers that could be possible factors. Okay, so the bigger the number is, the more numbers there are below it that might be able to multiply to give you that big number. So the bigger the numbers get, the sparser the primes become. So since there's fewer and fewer primes as you go through the numbers, it's reasonable to wonder, is there some biggest prime number? Once you're up to like a quadrillion or like, a quadrillion times a quadrillion, are there just so many numbers beneath that there are no prime numbers anymore? It's a reasonable question. And you could never know just by checking everything, since there's an infinite number of numbers. So here's an ancient theorem that was first proven, at least historically, by Euclid. Theorem: there are more primes than found in any finite list of the primes. The way that we would say this today is that there are an infinite number of primes, but the ancient Greeks didn't have the concept of infinity. So for example, today, students in a geometry class talk about lines that go forever in both directions. But ancient Greeks viewed lines as segments that could be extended indefinitely, but which were not something infinite that we're only viewing part of. Okay. So therefore, we'll state it like this, that if we have any finite list of primes, then there are more primes than that. The way that Euclid proves this uses a method known as proof by contradiction. That is, it makes a number of assumptions and then shows that these assumptions lead to a false conclusion. This means that the initial assumptions cannot all have been correct. Okay, so the assumption that we start with here is just that there are n primes, and we can write them all in a list. However many there are, if there is some largest prime, then this means that there are only some finite number in total. Let's call that number n, and write down a list of the primes, and label them p1, p2, p3, and pn. Okay, so this is how we're labeling the primes. So for example, p1 equals 2, since that was the first prime number. p2 equals 3, since that's the second prime number. p3 equals 5, since that's the third prime number. p4 equals 7, p5 equals 11, p6 equals 13, and so on. And pn is whatever the largest prime number is. Now, define this number p as the multiple of all of the primes in our list, plus 1. So P equals P1 times P2 times P3 times P4 times P5 up to Pn. Okay, so it's the product of all of the primes in our list. And then we add 1. So now there's 2 possibilities, all right? Either P is prime or not. If P is prime, then we found a new prime that wasn't on our list, because I can see that P is bigger than all of the primes on my list, right? Because it's a product of all of them plus 1. It's definitely bigger. So P wasn't on our list, and if P is prime, then we have a contradiction, which proves that our assumption that there were only n primes was false. However, maybe P isn't prime. But if P isn't prime, then by definition, that means that P has to be divisible by some prime. And let's call that prime which divides P, let's call it Q. All right? So now, this number Q cannot be any of the primes from our list, because if it were, then Q, when we divided P by Q, would give us remainder of 1. All right? So we know that Q does not, or is not one of the primes from our list, because when we divide P by Q, we get remainder 1. Right? We can see that from the form of Q. Right? So this prime Q is some prime that was not on our original list. So either way, the original list was incomplete. Either P was prime, and P wasn't on our list, or else Q was prime, some divisor of Q, and we know that none of the divisors of P are in our list. So either way, we have a new prime. And this proves that the original list was incomplete. Wow. So, and if the original list was incomplete, why is that true, since we were assuming it was all the primes? Well, what went wrong is our assumption that there were only some finite number. Okay, so this proves our theorem. There are more primes than found on any finite list of primes, and we're very happy we get to write QED. We proved it. All right. This is like a masterpiece of mathematics. Very exciting. Let's talk about another classic example. And remember, please ask any questions you have in the chat. Now let's talk about rational and irrational numbers. So a number is called rational if it can be expressed as a ratio. That is, n is rational if there exist integers p and q, such that n can be written as p divided by q. So for example, the number 7 is certainly rational because I can write it as 7 divided by 1. So p would equal 7 and q would equal 1. Or the number 2/3 would be rational because I could say p equals 2 and q equals 3. All right, so 2/3 would also be rational because p equals 2, q equals 3. Okay, p over q, where p is 2 and q is 3, that works too. And there was an ancient school of Greek mathematicians named the Pythagoreans. They were named after their leader, Pythagoras, who, as you may guess from his name, invented or discovered the Pythagorean theorem. So he was very famous, and there's like lots of stories about Pythagoras, and I guess he did some other cool stuff as well besides just the Pythagorean theorem. So everybody loved him, or at least he had these like followers. He had like a cult following of these like Greek mathematicians who like loved Pythagoras and like followed his teachings, and it was like a little bit cult-like. But they preached that all numbers could be expressed as the ratio of 2 integers. This was like part of the gospel of the Pythagoreans. A little bit hard to imagine today, but it was very important to them that all numbers could be expressed as a ratio of 2 integers. And this was sort of like a religious and emotional attachment of theirs. Well, one of the acolytes of this school, Hypasus, discovered that this was false. He discovered the existence of what we now call irrational numbers. The Pythagoreans were shocked by this discovery and considered it a heretical idea. They forbade Hypasus from sharing this knowledge with outsiders, but he did anyway. He shared this new forbidden knowledge that he had discovered, and the other Pythagoreans punished him by drowning him at sea, at least according to historical accounts that have survived to this day. And the image there is a German painting from the 1800s called "The Pythagoreans Greet the Dawn," or something like that. So those are supposed to be the Pythagoreans. All right. So let's look at this heretical discovery that Hypasus made 2,000 years ago, the discovery of irrational numbers. And I think this is something that you'll be capable of following. Hypasus probably proved this with geometry, but we're going to do an easier proof using algebra. In part just because you guys are going to see plenty of geometry proofs in your geometry class, so I'd rather show you something different. All right, so theorem, the square root of 2 is irrational. Remember, that means that there are no numbers p and q, such that we can write the square root of 2 as p divided by q. Here's the proof. Suppose that the square root of 2 is rational. So this is going to be another proof by contradiction. We're assuming that root 2 is rational, and we're going to get a contradiction, which proves that it is not rational. All right, so suppose there are two such numbers, p and q, such that the square root of 2 equals p divided by q. And suppose that this fraction p divided by q is in its most reduced form. That's the part that we're going to contradict later. If there really are two such numbers, p and q, then certainly we should be able to put them in their most reduced form. So assume that p and q are in their most reduced form. Now I can rearrange this equation. The square root of 2 equals p divided by q. Let me multiply both sides by q, and I get the square root of 2 times q equals p. Now I square both sides. This gives me 2q squared equals p squared. Thus, we see that p squared is an even number. Right? This goes back to our proofs from a couple of slides ago. Since p squared can be written as 2 times something, in this case q squared, that means that p squared is even. All right. And we proved earlier that the product of two odd numbers is always odd. So if p were odd, then p squared would be p times p, which would be odd times odd. So p squared would be odd also. But p is not odd. Or p squared is not odd, which means p cannot be odd. And therefore p must also be even. Okay, if p were odd, p squared would be odd, but it is not. Okay, so p must be even. This means we can write that p equals 2a for some integer a. That's the definition of an even number. So I can plug that definition into my formula. I can replace p by 2a since we now know that p is even. And that was one of the key steps here. So 2q squared equals 2a all squared. So 2q squared equals 4a squared. Okay, just distributing the square over the parentheses. Now I can divide both sides by 2 and divide both sides by a squared. This gives me that q squared over a squared equals 2. And then I can take the square root of both sides and conclude that q over a equals the square root of 2. But notice that q is smaller than p, because q was in the denominator of the original fraction, and the square root of 2 is bigger than 1, since 1 squared is 1, which is less than 4. Okay, so p is bigger than q. And likewise, I know that a is also smaller than q, because q squared divided by a squared equals 2. So this means that we assumed that p over q was in its most reduced form. But now we've simplified it to some reduced form q over a, where q is smaller than p and a is smaller than q. So since our original assumption would have been valid if the square root of 2 were rational, and since we disproved that original assumption, it must be the case that the square root of 2 is not rational. Or we could say that the square root of 2 is irrational. Okay? QED. We proved it. All right. Kind of a sneaky proof. And we managed to show something pretty incredible, that there's no pair of numbers p and q that we could use to write the square root of 2. All right. So again, please let me know if you have any questions. Just one last type of proof. This one's a little harder and I'll go through it a little more quickly. But just to give you a flavor of some other kinds of things that are out there, this is called proof by induction. This is a method of proof in which you prove a statement, you prove that it is true for some initial case called the base case, say a equals 1. Then you assume that the statement is true for a case a equals n, some arbitrary larger value of the parameter a, and prove that your statement, if it's true for a equals n, must therefore be true for a equals n plus 1. And since the value of n is arbitrary, this will then form a chain showing that if the statement is true for n equals 1, it must be true for n equals 2. Or if it's true for a equals 1, it must be true for a equals 2. But then if it's true for a equals 2, it's true for a equals 3. And then if it's true for a equals 3, it's true for a equals 4. So therefore, it would be true for all values of a. So that's a pretty cool principle. And I'll show how we could use this to prove that the number of subsets of a set with n elements is 2 to the n. So we'll do it by the inductive principle, or the principle of mathematical induction that we just defined. Note that if a equals 1, the set has so that means that the set just has a single element. And remember, we're trying to say how many different ways are there that we could arrange a subset of the elements of our set. So for example, like let's say that there's 10 people in a room. So there's 10 of us. The question here would be, how many ways are there to pick out some subset of these 10 people? So say I want to give, I'm going to put hats on some of these 10 people. How many different ways are there to choose who I give those 10 hats to? Okay, and the answer is going to be 2 to the 10th in that case. All right, let's prove it. So first, if there's just one person, say in our room, there are 2 ways that I could give hats to these people. I could either give the person a hat, or I could not give him a hat. Okay, so for the case a equals 1, so if a equals 1, I find that there are 2 to the first, 2 to the first equals 2 ways to take subsets of that set. And so our theorem is true for the case a equals 1. Now, assume the statement is true for a equals n, i.e. that a set with n elements has 2 to the n subsets. So then consider a set with n plus 1 elements, okay? And we'll label one of the elements p. There are 2 types of sets in S, those that contain p and those that do not. Of the sets that don't contain p, these are also subsets of a smaller set, which is S minus p, which has only n elements. Therefore, there are 2 to the n such sets. On the other hand, the sets which do contain p are also just subsets of that smaller set, S minus p, but with p also tacked on. So there are also 2 to the n of those types of sets as well. I know that part's a little confusing. But hence, in total, there are 2 to the n plus 2 to the n equals, 2 to the n plus 2 to the n equals 2 to the n plus 1 subsets of S, which proves that if it was true for n equals, for a equals n, it's also true for a equals n plus 1. And so therefore, our theorem must be true for all different values of n. All right. So that's an example of a really powerful method called proof by induction. It kind of almost seems like magic because you get to sort of assume it's true and then use that in the very proof that it's true. But the reason it works is we prove that it's true for the first case, and then we prove that if it's true for n, then it must be true for n plus 1. I know this last one was a little harder, so if it didn't make sense to you, don't worry about it. All right. So I wanted to end with the idea that there are many important open questions left in mathematics. For example, the Clay Mathematics Institute published a list of 7 important problems. Okay. Back in 2000, and offered a $1 million prize to the first person who could solve each of these problems. And the solution here means you have to prove it. So these are all conjectures, and if they're proven, they will become theorems. It's not too important what these 7 different theorems mean, but yeah, so far, only one of them has been proved, right? So the Poincare conjecture, check. Right? That was solved by a Russian mathematician some years ago. But the other 6 are all still open questions, and they're very important for the future of mathematics. And these are not the only 7 important problems. There are lots of other problems that remain open. So one day, many of these will be proved or disproved, right? Because we don't really know yet whether they're true. So one day these will be proved or disproved. And maybe you could be the one to do it. All right. So I'll leave it there. Let me know if you have any questions. I'd be happy to answer some questions. I hope that some of the methods of proof that we talked about here made some sense to you. And I also hope that it was fun. And I also hope that you take away a sense of this broader long-term historical perspective from which proofs allow math to grow over time as this multi-generational project, which has been going on for 2,000 years and will, I think, be going on for, if all goes well, thousands of years to come. All right, well, if there are no questions, I will just remind you that we meet here every Monday at 1 p.m. This Thursday, so just a couple of days from now, I'll be doing a session on physics. I know some of you had requested some science topics, so I'll be teaching a physics lesson this Thursday at the same time that this session took place, from starting at 1 p.m. Eastern time. So yeah, hopefully I'll see some of you there. And either way, thank you for joining, and I hope you had some fun and learned something as well. Thank you very much.